In 1944, German pilots began reporting something terrifying. American anti-aircraft shells were exploding near their aircraft. Without needing to score a direct hit, flak bursts appeared to follow aircraft through the sky, detonating at precisely the right moment for maximum damage. It seemed impossible, almost like magic. The Allies had developed a weapon so revolutionary that it would be called one of World War II's greatest inventions. This is the story of the proximity fuse. Since the invention of aircraft, military planners had struggled with a fundamental problem. How do you shoot down a fast-moving target flying thousands of feet in the air? Anti-aircraft artillery required extraordinary precision. Gunners had to calculate the aircraft's speed, altitude, and direction, then aim where the aircraft would be when the shell arrived, all while the aircraft maneuvered to avoid being hit. Traditional anti-aircraft shells used timed fuses. Gunners would set the fuse to explode at a specific altitude, based on their estimate of where the target would be. This system had severe limitations. If the timing was off by even a fraction of a second, the shell would explode harmlessly away from the target. Studies showed that it took an average of 2,500 shells to shoot down a single aircraft using timed fuses. This was an appalling rate of inefficiency. During the Battle of Britain, German bombers attacked with relative impunity. Anti-aircraft fire was largely ineffective. Most shells exploded nowhere near their targets. The psychological effect on defending troops was devastating. They could only watch as enemy aircraft flew overhead, knowing their defensive fire was mostly futile. What was needed was a shell that could detect its target and automatically explode at the optimal moment. A fuse that sensed proximity to the aircraft and detonated without human intervention. In 1940, both Britain and America began working on this problem. The British were focused on immediate survival. The Americans saw the strategic potential. What emerged would be one of the war's most closely guarded secrets, and one of its most effective weapons. The idea of a proximity fuse was not entirely new. Scientists had discussed the concept since World War I, but the technology to build one didn't exist. The basic principle was straightforward. The fuse would contain a miniature radio transmitter and receiver. As the shell approached a target, radio waves would reflect back. When the reflected signal reached a certain strength, the fuse would trigger the explosive. This would cause the shell to detonate at the precise moment for maximum damage to the aircraft. The challenges in building such a device were immense. First, everything had to fit inside a shell fuse, a space only about 5 inches long and 2 inches in diameter. Second, the fuse had to withstand incredible forces. When a shell is fired, it experiences acceleration of 20,000 times the force of gravity. This would instantly destroy any conventional electronics. Third, the fuse had to spin at incredibly high speeds. Artillery shells spin to maintain stability in flight. Some shells spin at over 500 revolutions per second. Fourth, the device needed its own power source. Batteries of the 1940s were too large and fragile. Fifth, it had to be reliable enough for military use. A dud rate of even 5% would be unacceptable. And finally, it had to be manufacturable by the millions, at a cost that wouldn't bankrupt the war effort. Most engineers considered these requirements impossible, but a team of brilliant scientists was about to prove them wrong. In 1940, the United States was not yet at war, but President Roosevelt knew American involvement was likely. He authorized the creation of the National Defense Research Committee. This committee brought together the nation's top scientists to work on military technology problems. Within this committee, a special division was created, Section T, standing for tubes. It was a deliberately vague name to hide the true purpose. Section T's mission was to develop the proximity fuse. The director was Merle Tuve, a physicist from the Carnegie Institution. Tuve assembled a team of exceptional engineers and scientists. Many came from universities, leaving promising academic careers. Others came from industry, bringing practical manufacturing knowledge. They worked at the Applied Physics Laboratory, a new facility built specifically for this project, located at Silver Spring, Maryland, outside Washington, D.C. The facility operated under intense secrecy. Workers were told only what they needed to know. Many didn't understand what they were building until after the war. The British shared their early research on proximity fuses, including photoelectric designs that proved impractical. The American team decided to focus on radio frequency detection. This approach seemed most promising for the conditions of combat. The team divided into specialized groups. One group worked on miniature vacuum tubes. These tubes had to be incredibly rugged and tiny. Another group designed the radio circuit, finding ways to make it survive artillery forces. A third group worked on the power supply, eventually developing a battery activated by the shell's spin. A fourth group handled the explosive mechanism, ensuring reliable detonation at the right moment. The work proceeded at an intense pace. Everyone understood that lives depended on their success, and that every day of delay meant more Allied casualties. The vacuum tube problem required revolutionary thinking. Standard vacuum tubes of the era were fragile glass devices. They would shatter instantly under artillery forces. The team needed tubes that could survive 20,000 times gravity, while remaining small enough to fit in a fuse. The solution came from reimagining tube construction entirely. Engineers designed tubes with extremely short, thick elements. The internal structures were reinforced and rigidly mounted. The glass envelope was made thicker and more robust. These tubes looked almost nothing like conventional vacuum tubes. They were nicknamed subminiature tubes. Each one was about the size of a pencil eraser. Testing these tubes was brutal and exhaustive. Engineers fired them in artillery shells to verify they survived. They spun them at high speeds to test rotational stability. They subjected them to temperature extremes and humidity. Each failure led to design improvements. The power supply presented another challenge. Chemical batteries wouldn't survive the shock of firing. The solution was elegantly simple. A reserve battery that was activated by the shell's rotation, an electrolyte solution was held separate from the battery cells. When the shell spun, centrifugal force pushed the electrolyte into the cells, activating the battery and providing power to the fuse. This meant the battery had virtually unlimited shelf life, and only activated when the shell was fired. The radio circuit design required incredible miniaturization. Every component had to be tiny yet robust. Resistors were specially manufactured to microscopic size. Capacitors were redesigned for strength and compactness. All connections had to withstand violent acceleration. Engineers developed new soldering and assembly techniques. Each fuse was hand-assembled with microscopic precision. Workers used magnifying glasses and specialized tools. Quality control was obsessively rigorous. By 1942, the team had a working prototype. It was designated the Variable Time Fuse, or VT fuse. The name was deliberately misleading to hide its true nature. Initial tests were promising but revealed new problems. Each problem was methodically solved through testing and refinement. By late 1942, the fuse was ready for combat trials. The proximity fuse was first used in combat in January 1943, but not over land as originally planned. Military planners feared that duds might fall into enemy hands. If the Germans captured an intact fuse, they could copy the technology or develop countermeasures against it. The solution was to use proximity fuses only over water, where duds would sink and be unrecoverable. Naval anti-aircraft guns were equipped with VT fuses first. The cruiser USS Helena received the first combat load. On January 5, 1943, Helena was off Guadalcanal when Japanese bombers attacked the American fleet. Helena's 5-inch guns opened fire with VT-fused shells. The results were immediately apparent and shocking. Shells exploded precisely near the attacking aircraft, without requiring the impossibly precise aiming of timed fuses. Multiple Japanese aircraft were shot down in rapid succession. The gunners were amazed at the effectiveness. Word spread quickly through the fleet. Ships clamored for the new secret ammunition. Production was ramped up as fast as possible. By mid-1943, VT fuses were standard on most American warships. The impact on naval air defense was revolutionary. Where it previously took thousands of shells to down an aircraft, VT fuses reduced this to an average of under 100 shells, a 20-fold improvement in effectiveness. Japanese pilots began to fear American anti-aircraft fire. Their losses mounted steadily. The Battle of the Philippine Sea in June 1944 demonstrated the proximity fuse's devastating effectiveness. American ships shot down hundreds of Japanese aircraft. The battle became known as the Great Marianas Turkey Shoot. VT fuses were a major factor in this lopsided victory. Japanese naval aviation never recovered from these losses. Creating a working prototype was one thing. Manufacturing millions of them was an entirely different challenge. Each proximity fuse contained over 200 components, many of which had to be custom-made to exacting specifications. The subminiature vacuum tubes alone required new manufacturing methods. Factories had to be built specifically to produce them. Workers needed training and techniques that didn't exist before. Assembly of the fuses was done primarily by women. Their smaller hands and attention to detail proved ideal for the microscopic work required. Each worker specialized in a specific assembly step. The fuse moved down a production line. With components added at each station, quality control inspectors checked work at every stage. A single defect could cause a fuse to fail, and failure in combat meant lives lost. Multiple companies were contracted to produce fuses. Western Electric was the primary manufacturer, but Eastman Kodak, Zenith, and others also produced them. At peak production, over 40,000 fuses were manufactured daily. This required coordination across hundreds of suppliers, each providing specialized components. The cost per fuse was approximately $20, about $300 in today's money. This was expensive but considered worthwhile. Given the dramatically improved effectiveness, by war's end, over 22 million proximity fuses had been produced. This represented one of the largest precision manufacturing efforts in American industrial history up to that time. In December 1944, Germany launched its last major offensive, the Battle of the Bulge in the Ardennes Forest. This would be the proximity fuse's first major test in ground combat. The restrictions on land use were finally lifted. Allied commanders deemed the tactical situation desperate enough to risk the enemy possibly capturing intact fuses. American artillery units received shipments of VT-fused shells, with strict orders about their use and security. The proximity fuse proved devastating against infantry. Traditional artillery shells exploded on contact with the ground. Much of their blast was absorbed by the earth. Soldiers in foxholes or behind cover were relatively safe, but proximity-fused shells exploded in the air, 10 to 20 feet above the ground. This created an airburst that showered deadly shrapnel downward. Foxholes provided no protection against this overhead attack. The psychological impact on German troops was severe. They had never experienced anything like it. German infantry advances were shattered by VT fuse barrages. Attacks that would have succeeded against conventional artillery were stopped cold by the airburst shells. At the Siege of Bastogne, American artillery used VT fuses to devastating effect against German assaults. The 101st Airborne, surrounded and outnumbered, held partly because proximity fuses multiplied their firepower. German prisoners interrogated after the battle spoke of the terror of the tree bursts. They called it the incredible disappearing American artillery because shells seemed to explode without hitting anything. General George Patton called the proximity fuse one of the three most important developments of the war, along with radar and the atomic bomb. Some military historians credit VT fuses with shortening the Battle of the Bulge by weeks and saving thousands of Allied lives. In the Pacific Theater, Japan introduced a terrifying new weapon. The kamikaze suicide aircraft deliberately crashed into ships. Kamikaze attacks began in earnest in late 1944. These attacks were devastatingly effective against conventional defenses. A pilot willing to die could often get through defensive fire. Even if damaged, a kamikaze might still reach its target. Traditional anti-aircraft fire required destroying the aircraft completely, a difficult task under the best circumstances. The proximity fuse changed the equation dramatically. VT-fused shells didn't need to destroy the kamikaze. They just needed to damage it enough to throw off its aim, or kill the pilot before he could complete his dive. Ships equipped with VT fuses had much better survival rates against kamikaze attacks than those using conventional ammunition. The Battle of Okinawa in 1945 saw the most intense kamikaze attacks of the war. Over 500 kamikaze sorties were flown against American ships. Proximity fuses were credited with saving dozens of vessels and thousands of American lives. Radar picket destroyers stationed around Okinawa were particularly vulnerable to kamikaze attack. These ships relied heavily on VT fuses for defense, creating a curtain of airburst fire around themselves. Japanese pilots learned to fear the shells that exploded precisely as they approached their targets. Many kamikazes were destroyed before completing their attacks. The proximity fuse's effectiveness against kamikazes was one reason the tactic ultimately failed. Despite causing significant damage and casualties, kamikaze attacks could not stop the American advance. After the war, Japanese officers acknowledged that American anti-aircraft effectiveness had shocked them. They had expected the kamikaze to be far more successful. The proximity fuse was a major factor in negating Japan's last desperate aerial weapon. Germany attempted to develop their own proximity fuse during the war. German scientists understood the concept and recognized its value. but they faced insurmountable technical challenges. German electronic component technology lagged behind America's. They couldn't produce vacuum tubes small and rugged enough. German attempts to copy captured Allied fuses failed. The manufacturing precision required was beyond their capability. By late 1944, Germany was also facing severe resource shortages. Strategic materials needed for electronics were unavailable. Factories were being bombed, disrupting production. German scientists did develop acoustic proximity fuses. These detected the sound of aircraft engines. But acoustic fuses were far less reliable than radio fuses. They were susceptible to interference from wind and other noises, and couldn't function effectively in the chaos of combat. A few German acoustic fuses saw limited combat use, but they never achieved the reliability of American VT fuses. The Germans also experimented with infrared proximity fuses, detecting the heat from aircraft engines. These showed some promise but were never fully developed. The war ended before Germany could field effective proximity fuses. This technological gap contributed to Allied air superiority. German aircraft faced increasingly deadly anti-aircraft fire, while Allied aircraft operated with relative safety. After the war, German scientists examined captured VT fuses. They marveled at the engineering and manufacturing quality, admitting they couldn't have produced anything equivalent, even if given unlimited time and resources. The proximity fuse was one of the most closely guarded secrets of World War II. Security around the project was extraordinary. The fuse was never mentioned by name in communications. Code names and euphemisms were used at all times. Workers at manufacturing plants knew only their specific task. They weren't told what the final product did or how it was used. Security officers monitored all personnel with access to the project. Unauthorized discussion could result in immediate termination, or even prosecution under wartime secrecy laws. Military units using VT fuses received special briefings. They were ordered to use them only over water, or in dire circumstances. To prevent the enemy from capturing intact examples, dud shells were to be recovered and destroyed whenever possible. Gunners were forbidden from discussing the fuses, even with other military personnel not authorized to know about them. The press was completely kept in the dark about proximity fuses. No mention appeared in newspapers or magazines during the war. This was a remarkable achievement in an era before official censorship. When reporters were generally cooperative with military secrecy, the public didn't learn about VT fuses until after victory in Europe. When the War Department finally released information, even then many technical details remained classified. The Germans apparently never fully understood how American anti-aircraft effectiveness had improved so dramatically. They suspected some kind of proximity detection, but never grasped the full details of VT fuse operation. This intelligence failure cost them dearly, both in aircraft losses and in their inability to develop countermeasures. The proximity fuse continued to evolve throughout the war. Early versions had limitations that engineers worked to overcome. The original Mark 32 fuse worked well against aircraft, but had reliability issues in certain conditions. The Mark 53 improved reliability and added safety features. It included a delay mechanism to prevent premature detonation and better resistance to accidental triggering. The Mark 45 was designed specifically for use over land, with modifications to prevent detonation from ground reflections until the shell reached optimal airburst height. Engineers also adapted the fuse for different caliber shells, from 3-inch naval guns to 155mm howitzers. Each application required modifications to the basic design. Specialized versions were developed for specific missions. Anti-shipping fuses optimized for low-altitude detection, high-altitude fuses for bomber defense, even experimental fuses for anti-tank rockets. The subminiature vacuum tubes were continually improved. Later versions were more rugged, more reliable, and easier to manufacture. Production techniques were refined to increase output and reduce costs without sacrificing quality. By war's end, proximity fuse technology was mature, reliable enough for routine military use, yet still advanced enough to maintain Allied advantage. The lessons learned in developing VT fuses would influence electronics engineering for decades. The proximity fuse's influence extended far beyond World War II. The technology became standard in post-war military arsenals. Modern versions continue to be used today. The Korean War saw extensive use of proximity fuses against Chinese and North Korean forces. Their effectiveness in the mountainous Korean terrain proved even greater than in World War II. The Vietnam War featured improved electronic proximity fuses, using transistors instead of vacuum tubes. These were smaller, more reliable, and less expensive. Modern proximity fuses use sophisticated microprocessors and can discriminate between different types of targets. Some can even be programmed for specific detonation parameters. The civilian applications of proximity fuse technology were equally significant. The subminiature vacuum tubes developed for VT fuses enabled the development of portable electronics. Early hearing aids used subminiature tubes, as did the first portable radios and test equipment. The manufacturing techniques developed for mass-producing fuses influenced the entire electronics industry. Quality control methods, precision assembly techniques, and miniaturization approaches all stem from VT fuse production. Radar technology benefited from proximity fuse development. The two technologies shared common components and principles. Engineers who worked on fuses often moved to radar projects, bringing their expertise in miniaturization and ruggedization. The proximity fuse also demonstrated the value of applied research during wartime. It showed that civilian scientists and engineers could make decisive contributions to military effectiveness. This lesson influenced post-war defense research organization, leading to institutions like DARPA that continue to develop breakthrough military technologies. Behind the technical achievement were thousands of dedicated individuals. Fuze, the director of Section T, worked tirelessly to coordinate the development effort. He balanced technical challenges with manufacturing realities and navigated military bureaucracy to keep the project moving. After the war, Fuze returned to basic research in physics, never seeking fame or recognition for his wartime work. Lawrence Hofstad was Fuze's deputy, a brilliant engineer who solved many practical problems. He later became a leader in atomic energy research. Ralph Baldwin designed many of the fuse circuits, working out how to make electronics survive artillery forces. His innovations in circuit design influenced post-war electronics. The subminiature tube team included some of America's best vacuum tube experts. They pushed the boundaries of what was possible, creating tubes that seemed to defy physics. The thousands of women who assembled fuses worked with dedication and precision. Many didn't learn what they'd built until after the war, but they took pride in knowing their work saved lives. Military personnel who used VT fuses in combat were often unaware of the technology's complexity. To them, it was simply ammunition that worked far better than anything they'd used before. Countless lives were saved by proximity fuses: sailors who survived kamikaze attacks, soldiers who weren't killed by German counterattacks, pilots who returned safely because enemy aircraft were shot down before reaching them. Most never knew they owed their survival to a team of engineers in Maryland who had solved an impossible problem. The Proximity Fuse project offers valuable lessons about technology development. First, seemingly impossible problems can be solved with sufficient resources and dedicated effort. The VT fuse required breakthroughs in multiple areas simultaneously, yet it went from concept to mass production in under 3 years. Second, interdisciplinary collaboration is essential. The fuse combined expertise in electronics, mechanical engineering, chemistry, ballistics, and manufacturing. No single discipline could have created it alone. Third, manufacturing must be considered from the start. The most brilliant design is worthless if it can't be mass-produced. Section T involved manufacturing experts early in the process. Fourth, testing under realistic conditions is crucial. The fuses were tested by actually firing them in artillery shells. This revealed problems that laboratory testing missed. Fifth, security can coexist with large-scale production, despite employing thousands of workers. The VT fuse remained secret throughout the war. Compartmentalization and need-to-know principles worked effectively. Sixth, civilian scientists can address military needs. Most Section T personnel had no military background, yet they created a weapon that changed warfare. Finally, technological advantage can be decisive. The proximity fuse gave Allied forces a significant edge that the enemy couldn't match or counter. These lessons remain relevant for modern technology development. Whether military or civilian, the proximity fuse's impact can be measured in cold statistics. Before VT fuses, shooting down an aircraft required an average of 2,500 anti-aircraft shells. With proximity fuses, this dropped to under 100 shells, a 25-fold improvement in effectiveness. In the Pacific Theater, proximity fuses accounted for over 50% of Japanese aircraft shot down by naval anti-aircraft fire. During the Battle of the Bulge, VT-fused artillery fire was estimated to be 5 times more effective than conventional ammunition. Against German infantry and vehicles, over 22 million proximity fuse were produced during the war, requiring the efforts of over 100,000 workers. The total cost of the VT Fuse program was approximately $1 billion in 1940s money, equivalent to about $18 billion today. This made it one of the most expensive weapons programs, second only to the Manhattan Project. But the return on investment was enormous. Military analysts estimated that proximity fuses shortened the war in Europe by several months and saved tens of thousands of Allied lives. The economic value of these saved lives and shortened war far exceeded the development and production costs. German forces lost thousands of aircraft and suffered massive casualties from VT fuse fire. These losses degraded German combat effectiveness and contributed to Allied victory. The proximity fuse was one of World War II's secret weapons. Unlike tanks or bombers, it couldn't be photographed in action. Unlike great battles, it generated no dramatic headlines. Yet its impact on the war was profound and measurable. The engineers of Section T accomplished what had seemed impossible at the war's beginning. They created a miniature electronic brain that could survive artillery forces and detect targets automatically, then mass-produced it by the millions. This achievement required innovation across multiple disciplines, from vacuum tube design to manufacturing techniques, from power supplies to safety mechanisms. The thousands who worked on proximity fuses